Perfect. I hope you are doing fine. We are going to talk about the palm. After the palm, we will talk about the exam a little bit, okay? For the palm, last time we stopped at net positive suction head available. Net positive suction head required. Any questions you have? No? No question for me? Okay. More on that palm. We talk about the equation, okay, head, how to read the crowd, how to convert from PSI to feet of water. Okay, all this we cover it, alright? And 0 PSIG to 34 feet. Anyone have any question on that? No? Okay, this is vapor pressure equation and Bernoulli equation for head system, 100 million equation, and we stop right about here, right? Okay, last time I get a question about H palm. Okay, H palm, how does that H palm look like? H palm, I have this picture, there's something inside in H palm that I can see that is multi-stage centrifugal pump. So that is H pump, and inside it have several centrifugal pump inside. Okay, H pump is multi-stage centrifugal pump. We put those pump in series to increase pressure. You agree? We increase pressure by doing that. Put them in series. Okay. I also have question about something else that I would like to have Mr. Bula discuss about it a little bit before we move on. I have this calculator, okay? It is a fancy one. It can do addition, okay, multiplication and so on. Is it good? All right. Why do I need to know how to do any of this when I already have a calculator? I don't, right? If I don't know how to do multiplication at all, I use my calculator. It will work just fine, is it? Maybe. You still, now you start to not trust me, right? Okay, all this pump, okay, compressor. Maybe we have the software. We know that, right? Okay, we have the software to do the compressor calculation. Put number of stage in, put discharge pressure, suction pressure, we get the answer. It's just a matter of click. Okay, we get everything out. Separator. Separator, what do we have on the separator? I believe we have some kind of chart or software. It's just one button or one phone call away. I call someone in the field, what do we use? They will tell me, and we get the right one. Isn't it like that? Yes. I think it's kind of the same thing on the calculator. Okay, I don't need to do it, know anything, I just use it. But maybe there are more to know about it. From the employer perspective, maybe I would like to invite Mr. Bula to discuss about this a little bit more on stage, please.
So I grew up without a computer. We had things called slide rules, and you've heard the stories of walking to school in the snow and things all uphill, right? So I admit things are a lot easier today. They're a lot faster. We expect instant results. We expect things to come to us just like that, and with a lot less work. And I know that's what you've seen as you've grown up. When you get in the workforce, there's going to be some reasons that you need to understand what are the underlying principles behind everything you do. Like being quiet in class, listening, being respectful, taking your part in a meeting, contributing your part and knowing when to be quiet. Those are all things that we can't teach in a classroom. They're things you're going to pick up on the job. But to the point of this class, why do we need to understand all this theory? Why do we have to go through a derivation? Why is it really necessary to get underneath all this when I've got a computer that just spits out an answer? So understanding why systems and machines work is really important when we have to do troubleshooting. A lot of troubleshooting is going to come in the form of a phone call. You're the engineer. It's going to come from the field. It's going to come from another group you may not even be working with. If you understand that theory that's underlying that, you can have a reasonable discussion with them. I'm working with electrical engineering and chemical engineering right now on some projects for OTC. And I don't propose to know all their underlying science of what they're doing. But they do expect for me to be able to talk to them reasonably, to understand the chemical principles or the electrical principles that are being tied together to make these machines and systems work. Can you make a reasonableness test? We have input information and we get an output. Can I look at that output and say that makes sense? Or do I just accept it at face value? It came out on the paper, came from a computer, it's got to be right. What were the underlying assumptions that went into that? And then you need to have a good enough recognition of that you can make that reasonableness test and say, this looks right, or something doesn't look right here, I better go back and check an input. I need to go back and get a little deeper into it. There's competition in the workplace too. Your employers are going to be looking for the best person to do the job. And so, can I distinguish myself from everyone else? Y'all are friends. Some of you may be going to work for the same company. And there's a lot of camaraderie that exists with that. But sooner or later, somebody's going to get promoted. And usually the one that gets promoted is the one that shows a grasp of what they're doing. That they do well in the job that they're in, and then they get that promotion. So, am I adding value? Is my understanding of what I'm supposed to do add value to the company? And employers will recognize that. And then you get that promotion. Now you're the boss. You're the supervisor or the supervisor in the field. And somebody lays a project on your desk, and I've got to look at it and say, yeah, that looks right. Because I understood what I had to go through to get to that point. Can I add value by asking the right questions? Do I know enough about this to bring out something that may be not right in the economics, or more importantly, is it not safe? Do I understand enough about this? If we went ahead and did this project this way, something unsafe is going to happen. We're going to have the wrong pressures in the system. We're going to have the wrong metallurgy. There's chemical reactions that will take place that we don't want. So all of those things are reasons to get a real firm base on where you're going. How long is it till graduation? 74 days. Everybody's got that number. That's a piece of data. And we get real good at collecting data. But data by itself doesn't tell us anything. Only when it becomes information is it useful. So we collect all that data, we get information. As we study information, it forms a progression where more and more it becomes knowledge. Knowledge is a useful tool. We put that knowledge together, we temper it with experience, and we get wisdom. So I want y'all to be wise. I want you to be able to take all this data, all these points together, develop it to wisdom. Because at my age, you forget it. And I'm relearning things every day and learning new things every day. But it all helps with a good, solid foundation. I want you to do well in your jobs. I'm a Texas Tech graduate, and the way you perform reflects on my degree and all the alumni and people that have gone before you. So we want you to understand, yeah, there may be a faster way to do this, there may be a simpler way, but do I know it? Do I understand it? Do I trust it? Can I add value and add value for my company and for me? Thanks.
All right, I think that helps for us to understand why do we all go through this thing. 59, Benjamin Bell, Joseph Black. Okay, that's your signature, right? Vedaste Kashumba, Sean Henderson, Colton Matas. All right.
Maybe interviewing her.
Yeah. I get some email from some of them. All right. We will try to go through this pump, okay, and the calculation about the pump, and hopefully you find enough reason that we learn about this. On Hazen-Williams equation, the restriction is about turbulent flow, water only, okay, and water at the pressure and temperature that they derive from. Okay. This is the final form of Hazen-Williams equation. Parameter C represent the roughness of the pipe. Okay. This equation tells me pressure loss in feet, okay, and with respect to diameter and volumetric flow rate, also length. So longer pipe has more pressure drop, correct? Smaller diameter has more pressure drop, okay? And higher flow rate has more pressure drop. So look at the diameter carefully. It's not just like 1 over diameter, it's diameter to the power 4.8. So diameter play a big role here. 1 over d to the power 4.8 is big. So when we go from 1 inch to 2 inch, okay, it's not that we cut the pressure drop in half. No, we cut the pressure drop by 2 to the power of 4.8. It's a lot. So when we go from half inch to 1 inch, it's a lot of pressure drop reduction. Okay, this is for water case. What about C value? C value, we have a table for that. New pipe has that C value. Okay, older pipe has lower C value. So because it gets rougher pipe cause more pressure drop. So this is the way that we estimate the pressure drop in the pipe. All right. In the test, it will be given. Okay, this is not part of this test, but will be for the final. Friction calculation. F sub m over there. Okay, this equation, by the way, please memorize it. Okay, pressure drop over length equal to F rho v squared over 2D. If that F is Moody friction factor. Okay, if it is standing friction factor, we don't have 2 over there, 2 will be on the top. Okay, this is just frictional pressure loss per unit length. If everything go in SI is Pascal second, okay, pressure drop in Pascal, kilogram per cubic meter, okay, then we get the answer in Pascal. The other P will be in Pascal. So this is based on Reynolds number. So friction factor come from a chart, okay? It can be laminar flow or turbulent flow. So this equation already take care of the flow regime, whether it's laminar flow or turbulent flow, right? And it's also take care of viscosity already. Which parameter is not included in this? What do you think? Or a little bit difficult to include in this? Anyone want to help me? Zachary M. Block. Zach, where are you? Which parameter is not in this equation?
I don't know.
Okay, is this fall far away from the inlet or close to the inlet? Or it doesn't matter? Doesn't matter. Okay, this equation most of the time is for far away from the inlet, fully developed flow, because this F sub m, most of the time when we look at the Moody diagram, it will be for fully developed flow. Okay, close to the inlet, we can have something else. The pressure drop per unit length doesn't need to be the same as this equation. It could be more, okay? It could be a lot more, okay? Or sometimes it could be less, depending on the inlet shape, all right? So this equation, most of the time is for fully developed flow. If we want to calculate developing flow, this F sub m has to be modified. Developing flow means shape of velocity profile keeps changing with distance. Okay, that is developing flow. Think about laminar flow. Laminar flow is a parabolic shape. At the inlet, everything comes out at the same speed. So we have this kind of shape, like a plug flow. Eventually, far away from the inlet, we will have parabolic shape. It takes some distance, okay, to change that shape of the velocity profile. I mean radial velocity profile. So some of the energy has to be spent to change the shape. After this point, the shape stays the same. It stays as parabolic shape. There is no additional energy that has to spend to change the shape of the velocity profile. Okay, so this part is likely to have more pressure drop. All right. But sometimes there's some kind of expansion. So if we go from the small pipe, have some expansion, when it is this case, it's a little bit hard to guess. Okay, it could be if this expansion is gradual expansion, like slowly change, gradual expansion. So we have high velocity over here, but lower velocity over there. So from Bernoulli equation, a higher velocity has like less pressure drop. You believe this? Higher velocity has less pressure drop. You don't believe it? Have you ever played this? You see the paper moving up? Try for yourself. The paper moving up. And the reason for that is because at the bottom, there is a stationary air. Air doesn't move at the bottom, right? But at the top, air keep moving. So when we have high velocity air on the top, it creates kind of lower pressure, and then the paper lifts up. Same way over here, when there's this expansion, there's a gradual change of the velocity. Velocity going down, there's a deceleration. Velocity going down, right? When velocity going down, we can gain pressure. Okay. At the same time, if we have this kind of pipe shape, okay, the fluid coming in, this is expansion, but it's sudden expansion, it's expand right away. So we create some kind of vortex over here, eddies and circulating motion. This thing causes a pressure drop, all right? So for gradual expansion, it can get pressure, but for sudden expansion, we lost pressure. So this means that near the inlet, if it is turbulent flow, inlet shape, inlet configuration is matter. Okay? So most of the time this equation is for fully developed. Fully developed means dV by dz is 0. There is no change of the shape of the velocity profile with the axial length. Got it? Okay. Maybe there's another concept that we should be aware of is about steady state. Steady state is not the same as fully developed. Fully developed means velocity doesn't change with length anymore. Okay? Steady state means it doesn't change with time. Okay? Is this equation for steady state or transient? Zachary or Ricky? Is it steady state or transient? Steady state. We have to turn on the pump for a while, then that equation applies, right? Right at the start, it's not that equation. Got it? So for transient include start, stop, change in the flow rate. Anytime that there is a change, that equation doesn't work. Okay? But it is asymptotic line. After a while, it will reach that point. So let's take a look for flow in a pipe. At the beginning, everything stops, no movement. When we turn on the pump, everything moves at the same time, right? So after a while, it arranges itself from stop to move, okay, at the speed of the speed of sound, very quick, okay. So that is transient during the startup. Speed of sound seems to be quick enough, right? So this is incompressible fluid. For the incompressible fluid, each molecule communicates at the speed of sound. But okay, let's say I have a subsea pipeline which is 50 miles, 100 miles. Speed of sound will have some delay, okay? It's not like I turn it on at this end and it will move at another end right away. No, it takes at most, like as fast as it can is the speed of sound, okay? That is the best that it can do. All right, we discussed this already. It's for steady state, fully developed, okay? It's for both laminar and turbulent. What about Reynolds number? You see this Reynolds number, rho V over mu, okay? Everyone have that. Look at the fluid property, rho and mu. This fluid property change with temperature. It's not constant, okay? So for onshore operation, we have flow in the line. We buried the pipe below the freezing line at 18 feet below the ground or something. Is it feet or inches? Inches, 18 inches below the ground. Then we don't have to worry about the temperature change, right? Okay, that's easy. For a subsea pipeline, it is insulated, if not buried. Okay, it's always insulated, but there is a temperature loss, there's a heat loss to the environment in a subsea pipeline. So this means at the wellhead, it may come hot at 130 Fahrenheit, but subsea condition is 40 Fahrenheit. It flows for a while, it gets colder and colder and colder. So when it gets colder or temperature drop, what happened to the viscosity? Go up or go down? Go up exponentially. Okay. When it's getting cold, it's a lot more viscous. Okay. Than it hot. So when it gets cold, it gets thicker. So viscosity at this location is maybe 10 centipoise. Over here, maybe 30 centipoise because of the change of the temperature. So in that case, can we still use this equation to estimate the pressure drop? Can we? What's your name? Caesar. Can we still use it? So can we still use this equation when the viscosity keeps changing with distance? Maybe? Maybe not. What do we do? What do we do? Daniel, right? What do we do? I quit my job because I cannot do this or what. The equations still apply, alright? But we can do the approximation. We may say, one of the section, this part, okay, viscosity is 10, this part, viscosity is 30. So when viscosity is 10, I calculate Reynolds number for that, then calculate pressure drop. When viscosity is 30, I calculate Reynolds number for that and calculate pressure drop. Get both pressure drop, add them together, it's a total pressure drop. Good? So this means we have to break the pipe, okay, when there's a change of the fluid property over time. Over here it's still available, sir. Okay, so this equation can be used for the change of fluid property with respect to pressure. What else can change in terms of fluid property? There could be some phase change, right? When we have the flow, there's a pressure drop. When we have pressure drop, gas can come out of liquid phase. We may, at the beginning, we may not have multi-phase flow. We may not have two-phase flow. We may just have liquid. But once it flows for a while, there's enough pressure drop. we can have gas phase coming out. Oh, Arif, can this equation be used for vertical flow, like flow in a well, to estimate frictional pressure loss? Or it's not, it's only for pipeline?
It doesn't have the term gravity in it,
It doesn't have.
so I'm guessing it can be used.
Okay. For the term with the gravity, we will have that delta H thing. The friction part stay the same. Okay, so the friction part for flow in the well is still this equation. Okay. Can it be used for gas phase, or this is only for liquid? It can be used for gas, but we don't. Okay, because it will be, most of the time it will be inaccurate. For the gas flow, when there's a pressure drop, temperature change, right? There's like JT cooling, right? So when the JT cooling, we have to discretize. Okay, when we have pressure drop, density of gas is from PV equal to CNRT. So density also change, right? It is correct, but it's not suitable for gas phase. If we really want to use it, we have to discretize, account for the change on the density or everything. So for gas phase, we have like panhandle B to use to do the calculation of pressure drop. It will be easier to use. But this equation theoretically is also applicable for the gas phase too. Okay, the length, everything we can use it, right? Very easy. Can we do it for the field unit? Instead of kilogram per cubic meter, if we decide to put pound per gallon or pound per cubic foot, there has to be some factor pop up over there. You can estimate or calculate that value, right? Yes. Okay, let's move on. This is about calculation of Reynolds number in the field unit. Okay. Centistroke, new. This is not V. Okay, it's new. So new is centistroke. What is centistroke? It's not mu, right? It's mu over rho. That is kinematic viscosity. That is new centistroke. Centistroke is length square over second. Okay, the dimension is length square over second. So that is centistroke. Do the math, is that kind of unit. We will have this conversion factor. So this is how it is derived. Alright? So your job is what? Find out what is centistroke. Is that millimeter square over second? Or is something else? Or is meter square per second? So that's your job to Google it, okay? But I'm pretty sure that conversion factor is okay. Centistroke sometimes is not that convenient for us to use. Sometimes we have to use centipoise, right? Centipoise is kind of centistroke modified by rho. Okay. I think we will show that later. Okay, frictional pressure loss, do some unit conversion, we can get this equation. Okay. Loss in height multiplied by multi-friction factor, velocity square over 2g and g sub c. G sub c is just a conversion factor. It's not like gravitational acceleration or anything like that. It is, but it is there just for unit conversion. The unit of g sub c is that unit. Okay, that is just for unit conversion. Okay, this is how to estimate the loss for height. Full form. What if we have something else? Something else means we have the change in the elevation, we go up. Okay, we pump uphill. Okay, we have the change in the velocity, we have the change in the pressure, we have work done by the pump. Okay, that is horsepower term, right? We have frictional pressure loss, and we have E sub V term, accelerational pressure loss. Accelerational pressure loss, or E sub V, happen to account for any loss due to acceleration, or any time that we create any eddies or vortex. That kind of loss comes from the change in the momentum. When we change the direction, we have the pipe the pipe is 90-degree elbow. Okay, when it reaches 90-degree elbow, it has E sub V, acceleration of pressure loss. Okay. When we have 45-degree elbow, we have another loss. We have a valve, it has another loss. Okay. E sub V term, people do experiment on it already, and it comes from a table like this. So it doesn't have unit. Okay. Rounded entrance pipe is that much. Sudden contraction, sudden expansion, orifice, sharp edge, 90-degree elbow, 45-degree elbow, it is square, it is round. So there are value of E sub V. Sometimes it is a range, okay? 1.3 to 1.9, for example. What do I use if it is a range? I use the conservative one, okay? I use the maximum value, so that maximum value will tell me the maximum loss, and I will kind of estimate the maximum possible horsepower that I need, okay? All right, that's E sub V term. Let's take a look at the unit. Okay, this equation, every term has the same unit. Do you believe me? Maybe. Okay, V is feet per second. G sub C is that. Okay, H is feet, and over here is G over G sub C. P is feet too, and we have G over G sub C. Okay, this is a for field unit. Let's take a look at the unit one by one. Okay, V square is feet square per second square. Good, that is V square. G sub C. G sub C is power mass foot per power force second square. So I put it over here. That is G sub C. And we have second square times over second square. At the end I have power force per power mass multiplied by foot. Okay, that is this term, the unit of that term. Power force foot per power mass. Every other term I get the same thing. Okay, they are the same thing for every other term. So this is where we have same unit. What about W hat? Work done by pump, right? Work done by pump. W hat is not BTU, not BTU per hour. It is some weird unit. Feet square per second square. Okay, that is work done per unit mass. Feet square per second square. So if I want a horsepower, I have to multiply kind of density and do some kind of unit conversion. All right. We will see for the example. And this is to show all those units. Okay, W hat multiplied by volumetric flow rate. Okay, W hat is feet square per second square. That is W hat. Feet square over second square multiplied by volumetric flow rate. Okay, it will give me this power force foot per second of power. Okay. And W hat is work done per unit volume, and that is what it is. All right, let's go through the example. Actually, it's a little bit more. You see, Wm hat and W hat. So over here is Wm hat, but over there, Wm hat is not W hat. Okay, Wm hat divided by G sub C multiplied by rho at the pump equal to W hat. Okay, so it's a little bit of conversion. We will see the example to see how do we actually do that. So this equation taking care of everything. Is this different? Has anything different than the equation that we had before? We previously had pump horsepower, right? Did we? MPSHA. Okay, horsepower. Look at this. Head multiplied by capacity multiplied by density. But what is the difference between this and that? So this, it gives me pump horsepower. I just need to know head, right? I just need to know the flow rate, density, and everything will be just fine. It gives me horsepower. Another one is a lot more. It has every other terms. So I would ask myself, what is the difference between that previous equation and this one? So this equation account for everything. How do I know how many feet of head do I have? Previously I need head, right? I'm sorry, I'm going back again. So previously we have this head in feet. What is that head in feet? Differential pressure, right? From the suction and discharge. How do I know how much pressure on the discharge do I need? How much is the discharge pressure do I need to perform a certain service? So the discharge pressure will be dependent upon frictional pressure loss, gravitational pressure loss, and any accelerational pressure loss or the change in the velocity. This equation tell me the way to calculate the required discharge pressure. Okay. Previously, I have to tell discharge pressure, right? Equation is easy and quick. But this time, if I don't know how much is the discharge pressure required, I can calculate it. Discharge pressure should be enough to overcome frictional pressure loss, accelerational pressure loss, the pressure loss due to the change in the velocity, the change in the elevation. Okay? So this equation take care of everything. If we already know the required discharge pressure, we don't need to do this. Okay? But if we don't know, like in the example that we are about to see, like in this one, then you have to do that. This, by the way, I believe is the same as fluid mechanics that you may take before. Is it? Is it the same? Yes, we could have it again. Alright. Okay, let me go through it quickly. What is the required power output for the pump at steady state in the system shown below? Water at 68 Fahrenheit and viscosity and density is given, is to be delivered from upper tank to the upper tank at that rate. Okay, 12 cubic foot per minute. All of the piping is 4-inch, internal diameter, smooth, circular pipe. Okay, how do I do this? I need Reynolds number in the pipe, right? So from the Reynolds number, before I do Reynolds number, I need velocity in the pipe. Velocity in the pipe, this time is not gas, it's just liquid. For the gas, we have the equation, do you remember? 60 multiplied by something to give me the actual velocity. So this time it's just liquid. The change in pressure doesn't change the liquid volume. Okay, we assume incompressible. Okay, it doesn't expand or anything. That's our assumption. So what we do is we calculate velocity from Q of flow rate over pipe cross-section area. Q over A give me velocity. Rho VD over mu give me Reynolds number. Well, let's take a look at how we do it. Okay. Step 1, get the velocity. Step 2, get Reynolds number. Then calculate motive friction factor and accelerational pressure loss coefficient is sub V. And calculate W hat over GC. Okay, W hat over GC. Then to get the energy of the pump per unit mass of the liquid. Power force foot per pound mass. Okay? Because every other term is power force foot per pound mass, like this equation give me. So we don't really calculate W hat sub n, we calculate the whole term, power force foot per pound mass. After that, multiply the mass flow rate, pound mass per second, with this, okay, to get power in unit of pound force foot per second. Is that power? Is it power? Force multiplied distance is energy. Energy divided by time is power. Alright? So we get that term, we multiply with the mass flow rate. Then we get power in that unit. And later on we can convert that to horsepower. This is how we use equation. Any question on this strategy? Any question you want to ask me? Okay, let's go through it. Velocity Q over A. Q over A is, how much is my Q? 12 cubic foot per minute. Okay, we have to do per second, so that is 12 over 60. Pi d squared over 4 I have 4-inch pipe. I want everything to be in feet, so it's 4/12 is D, right? So pi d squared over 4, at the end I get 2.3 feet per second. Reynolds number, rho v d over mu. Unit has to be consistent. D has to be in foot. Okay. I have D rho v over mu. So